Hello, this is Stat134 Lecture 1. Today in class, I gave an announcement, I gave a brief introduction, and then we talked about equally likely outcomes, interpretations, and started section 1.3 on distributions. For announcements, lab starts on Friday. The class website is stat134.org, where you'll find all important information. And I wanted to share with you an insightful previous student advice to you. Make sure you understand everything before even going to lecture. It helps with getting new concepts. Well, maybe that's going a bit too far, but it would be great if you could read ahead. So take a look at the schedule on the website. It always tells you what's coming up, and try and read ahead of where we are. It's going to make things go a lot smoother for you. My office hours is in the SLC Student Learning Center after class. The adjunct class 198 starts tomorrow, Thursday. You should contact Mike Leong. His email is given here. Introduction. So we started and I asked you guys which of these slides represents statistics and which probability. And you correctly said the second one represents probability, where we reach into a pail with a known distribution of marbles, and we can answer questions like, what's the chance of getting at least one marble of each color? The inverse of this process is statistics, or inferential statistics, where we don't know what the population is. We take a sample and we infer what the population is. So it's important, probability is an important engine for statistics. So we start off talking about equally likely outcomes, and this is a situation where all the outcomes in your outcome space are equally likely, and the probability of an event is just some collection of outcomes, is then the fraction of the number of outcomes over the total number of possible outcomes. In other words, the size of your sample space. So for example, if you have a 3-card deck, Jack, Queen, and King, what's the probability that the second card is a Queen? Well, so here I'm not conditioning at all on what the first or the third card is. This is an unconditional probability question, and A here is the event that the second card is a Queen. So we're just focusing on what the second card is, and so that has size 1, namely that the second card is a Queen. The sample space, however, allows the second card to be any one of 3 possibilities, Jack, Queen, or King. So the size of the sample space is 3, and hence the probability is 1/3. Just a quick review of a little bit about cards. We have 4 suits: heart, clubs, diamonds, and spades, and 13 ranks: ace, 2 through 10, and Jack, Queen, King for each suit, giving a total of 52 cards. We gave an example from the book where we shuffle a deck and the top 2 cards are dealt. What's the chance that you get at least one ace among the 2 cards? So here, there are a couple different ways to do it. One way to do it is to recognize, okay, one, that all outcomes are equally likely, and the size of our event consists of all pairs of cards with at least one ace. So we could have ace-ace, we could have ace non-ace, we could have a non-ace-ace. The chance of getting 2 aces in a row is 4 times 3. One way to see that is if you make a tree diagram. We have a chain of events. So the first card, to be an ace, it could be any one of 4 aces. So I'm looking here at this tree diagram, and then following each ace that you first get, there are 3 possible further aces that you can get, giving a total of 12 branches or 12 pairs of ace-ace combinations. So that's why we get 4 times 3. And similarly, ace, non-ace, non-ace, ace are 4 times 48, 48 times 4. And then the size of the outcome space is 52 times 51. So then the size of A is 4 times 99, and the size of the outcome space is 52 times 51, giving the probability of A is 0.149. Another way to do this is to use what's called the complement rule, and that's something we'll see next time. Or actually, no, we do it today, so we'll see a little bit later. And that's where we compute the probability that we get A complement. So A with a C on top means the complement of A, or the opposite of A. So the opposite of our event A is that we don't get any aces in the pair. So the chance of that is 48 times 47. So divided by 52 over 51, and then so it's 1 minus that to give us the same answer. So that's obviously a lot quicker. Interpretations of probability, well, we have two. The frequency interpretation and the subjective interpretation. For examples where you have where you can repeat an experiment many times with independent trials, you can interpret the probability as the limit of some relative frequency of the size of A to omega. So, for example, if you perform the first example where we have that 3-card deck and you're looking for the probability of getting a queen for your second card, which is 1/3, if you perform this experiment 1,000 times, right, you would expect then roughly to get around 333 times that you would get a queen for the second card, and out of 1,000, right? So now this interpretation doesn't work sometimes. For example, if you're asked for the probability of a particular patient surviving an operation, this obviously you couldn't repeat 1,000 times, so because it's a particular patient. So we rely then on conditional probability, which is a topic that we'll take up soon. And your probabilistic opinion may change over time as you acquire new data about your patient. Perhaps you learn something about them, that they're healthy or not healthy and so on, that might change that probability. On to section 1.3, distribution. So now we're going to allow the outcomes to have different probabilities. So we start off with an outcome space, and we assign to each element of your outcome space a non-negative number and require all the numbers to add up to 1. So we can build up probability from 3 axioms written here. And I'll just note the third one, which is called the addition rule, says that if A and B are mutually exclusive or disjoint sets, which means that they're not touching in this Venn diagram here, then the probability of the union is just the sum of the probabilities. You can just think of probability as an area in a Venn diagram of some event. So because the events aren't touching, they have no overlap, we can just add the areas. As another example, consider a die with a shape such that its width is this variable t, and so suppose the thickness of the die t is such that the chance of landing flat is either 2/3. So the chance of getting either a 1 or a 6 is 2/3. Find the probability distribution of the shape and make a histogram. So let's just note here that the chance of getting a 1 or a 6 is equally likely, as is the chance of getting 2, 3, 4, and 5. Just from the geometry, you can see that that's the case. And so we know that the outcome of getting a 1 and a 6 are mutually exclusive. So by the addition rule, 2/3 is the sum of the probability of 1 plus the probability of 6. Probability of 1 equals the probability of 6, hence they're each 1/3. And because all the probabilities have to add up to 1, we know that the other 4 probabilities is all 1/12. And I can make a histogram of this. Let's take a look at some rules. The difference rule, suppose that B is a subset of A. Then if B is a subset of A, we can draw it as so. Then the probability of A minus B, I'll just write it this way, or A intersection B complement, which is, they're both the same thing, they're the shaded region here, is probability of A minus the probability of B. It's kind of obvious from, you're just subtracting the area of B from the area of A, but if you want to follow your axioms, note that B union A minus B that's a disjoint union. And so then the probability of A is equal to the probability of B plus the probability of A minus B by the addition rule. We also have the complement rule. So the probability of the complement of B is just 1 minus the probability of B. Here, just let A be your outcome space, and then you're just going to apply the difference formula. Inclusion, exclusion, that's a good one. So now we allow A and B to intersect, and it says the probability of A union B is the probability of A plus the probability of B minus the probability of their intersection. Intuitively, it's clear that you need to subtract the probability of the intersection because you've sort of double counted it. The A includes the intersection and as well B includes the intersection. But if you want to derive it, you can just argue that the union of A and B is the disjoint union of A and B minus A, B. So when I write A, B here, I mean this is A, B, right? The intersection. Oh, that's, oh, sorry, we didn't do this, so I will skip over this. So we ended with Boole's inequality, which says that the probability of the union of some events AI is less than or equal to the sum of the probabilities of the AIs. So for example, if n is 3, this is saying the probability of A1 union A2 union A3 is less than or equal to the sum of all these probabilities. But we're going to show this for any n. Whenever it says you want to show something for any n, you need to prove it by induction. And so we will continue this next time. Have a great day.